Okay, thank you for the help on the technical difficulties. Let us go ahead. My name is indeed Julien Guinot, and with my co-author Alain Riou, we'll be presenting SLAP, Siamese Language-Audio Pretraining, without negative samples for music understanding. This work concerns itself with joint audio and text embedding spaces. I'm going to move a bit so I can see the screen. The idea behind which is to maximize the similarity between an audio clip and its corresponding textual caption. Learner representations through joint multimodal audio and text embedding spaces can then be strong representations for downstream musical tasks or textual tasks. They can also serve for text audio retrieval, recommender systems, zero-shot classification, or even, more recently, as the backbone of multimodal LLMs or of text condition generative systems. Typically, these representations are learned through text-music contrastive learning. In contrastive learning, which you might know as CLAP, the similarity for positive audio and text pairs is maximized, while the similarity for negative audio-text pairs is minimized. This is done through the contrastive normalized temperature cross-entropy loss, which you see on the right of the screen. This loss, however, has some intrinsic scalability issues. Empirically, we know that scaling representations, or scaling the batch size, leads to better representations. But to scale the batch size, we need to collect the similarity of audio and text embeddings along rows or columns of the pairwise similarity matrix. So we need to store this large B-squared matrix on a single GPU. So that comparison is directly an issue for scalability and performance. Another drawback of contrastive text music models is the modality gap, which is a phenomenon in which learned embeddings for different modalities lie on disjoint manifolds of the hypersphere, which empirically leads to poor performance on retrieval, poor performance on multimodal conditioning, and as well, intuitively, a poor joint understanding of the space.
And in multimodal SSL, they have already managed these issues of negative samples, and they managed, in particular, to prevent it with papers such as BIOL, so bootstrapped on latent, when their idea is that instead of having negative samples, you have two versions of the encoder, so with a student-teacher architecture, so you have your student encoder on the top, and a teacher encoder whose weights are just an updated moving average of the ones of the student. And to prevent collapse, you have in addition a predictor that maps the output of the the student to the output of the teacher. But so far there has not been any multimodal BIOL, and the reason why is that you cannot really make a moving average of between the encoders if it's two different modalities. So that's why it didn't exist until very recently, because that's the idea of our paper, SLAP, which is two BIOLs for two modalities. So first, you have this BIOL model that I presented just before, with for the audio modality, so with the standard loss here. You have exactly the same idea for the text, so one BIOL for audio, one BIOL for text, and in addition, you have these new intermodal losses that connect the two modalities. So the idea is that you have actually the intermodal losses here in purple that connect the two BIOL for the modalities, and the intramodal losses for audio and for text. And how does it perform? So to know that, we train our data on a big data set of 250K full-track caption pairs, and we evaluate on two standard benchmarks, so namely music caps first and song describer. So song describer is quite interesting because it's very high-quality captions made by experts, so it's more reliable results. And what we observe first is that if you take exactly the same model, so same architecture, same training data, trained from scratch, both models, what you observe is that on retrieval, SLAP consistently outperforms CLAP. But sometimes, and no, always actually, if you train CLAP, it's better to have first pre-trained encoders for both the audio and the text. And we observe also in this scenario that if you use pre-trained encoders, you get also better performances with SLAP compared to CLAP. We also compare with existing models such as Muscle and Lion Clap and observe better performances than these two existing models, in particular on the song describer dataset, which is the more interesting for us. In addition, we evaluate our model on zero-shot classification. So the idea here is that you compare the position of the audio embeddings compared to the text embeddings. So here, text embeddings can be classes such as genres or instruments. And the idea is that for each audio embedding, you're interested in what is the closest text embedding. So the red points here are the text embeddings, the blue points are the audio embeddings. And yeah, you can see these bold numbers that we outperform CLAP, and we also outperform the previous musical.
Okay, so we are happy because SLAP outperforms CLAP on both retrieval and zero-shot probing. But SLAP also has some very attractive attributes other than that performance. First of all, SLAP completely reduces the modality gap. Qualitatively, we can see here that on private caps, which is our internal test data set, there are distinct manifolds for the different modalities. If we plot those same embeddings with SLAP, we see that the modality gap completely disappears, and this promotes a true joint understanding, which is reflected, obviously, in the performance. We don't only evaluate the modality gap qualitatively, we also look at quantitative numbers. Notably, we evaluate two things. We evaluate the distance between the centroids of each modality. A larger distance correlates to a larger modality gap because that means the modalities are more separated. We also train a lightweight linear predictor to predict the modality of embeddings. Here, the lower the accuracy of this predictor, the less separated, the modalities are, because the predictor is having a harder time distinguishing between modalities. And we can see that across metrics and across data sets, once again, SLAP outperforms CLAP, with CLAP having completely disjoint modalities and SLAP having a true joint understanding. Another thing we tried is scalability experiments. Notably, SLAP, due to the lack of negative samples, has a new loss function that is open to gradient accumulation. Gradient accumulation is a technique that is used by accumulating gradients over the steps of training to artificially increase the batch size. So what we found is that we could artificially increase the batch size of SLAP during training and see similar improvements to performance on CLAP when actually scaling the batch size. And the kick here is that all of this training for SLAP is actually done on a single GPU, which is really nice. Okay, finally, we took a look at how the different losses terms, intermodal and intramodal, interact between each other during training. So what we looked at is the performance and the modality gap for different lambda values, which balances the intermodal and intramodal losses. We found two things. The first is that the best performance coincides with the smallest modality gap. Kind of expected, but we're still happy to find this. But also, the smallest modality gap occurs for balanced losses, and for extreme values of lambda, our model collapses. So I would like to propose to you an interpretation of why this is. Essentially, the outputs of the predictors are being pulled equally in either direction towards the modalities of the outputs of the projector of the teacher model. But the teacher model is updated more slowly, so there's higher inertia. So essentially, being pulled equally in either direction by heavier objects, the outputs of the predictors end up lying in the middle, which promotes this true joint understanding with no modality gap.
Okay, so to sum up, a few takeaways about SLAP. So what SLAP offers is first improved performance over CLAP, both on retrieval tasks, on zero-shot classification, as we show. We observe the absence of modality, or very limited modality gap compared to CLAP, which is a very valuable property, and we evaluated this both qualitatively and quantitatively. In addition, thanks to gradient accumulation, you can scale to very higher batch size without increasing your compute resources, which is a key element of SLAP compared to CLAP, because of this B-square matrix, this made CLAP very hard to scale before. And yeah, by the way, something that's quite interesting. So I know that everyone here is interested in music, so we did all the experiments on music. But as you may have seen, there is no assumption regarding the modality here. So probably SLAP could work also on image, on audio, and on any arbitrary modality. And every work that has been done before to improve the quality of these CLAP models could probably, well, actually will improve SLAP as well. So thanks a lot for your attention. And if you have any questions, please come to see us at the poster.